So the presentation topic is effect of electrodes and electrolytes on supercapacitance. So unlike a ceramic or electrolytic capacitor, a supercapacitor does not have a dielectric. Instead, it uses the elect electrical double layer that is formed at the interface of the solid, that means electrode, and liquid electrolyte. So here the figure 1 is a representation of the structure of the supercapacitor. A typical supercapacitor is composed of electrodes and electrolytes and a separator. The separator is used for preventing contact between the positive and negative electrodes. The electrodes are positioned in the electricity collector and coated with activated carbon powder. An electrical double layer is formed at each interface where the active carbon powder contacts the electrolyte. When we charge the supercapacitor, the negative ions and vacancies on the positive electrode side and the positive ions and the electrons on the negative electrode side are arranged across the interface. This state is arranged of ions and electrons, so it is called an electrical double layer. Supercapacitors are found in a variety of basic shapes and structures. A small and slim package discharging time can be varied according to packaging. Since the charging and discharging mechanism does not involve a chemical reaction, it is possible to charge and discharge more than 100,000 times. The reason for using activated uh, carbon on the electrode is to increase the surface area. Increasing surface area of the electrode influences obtaining a higher capacitance. As we see, this capacitance is calculated on the electrode. It is proportional to the electrode surface. Very fine pores on the activated carbon surface greatly increase the surface area of the electrode. Since the greater the surface area, the greater the charge that can be stored. The supercapacitor is able to achieve very high capacitance. The pores which have size longer than the ions with the solvation shell are advantageous in order to reduce the relaxation constant, which describes the minimum time required to obtain all the energy stored in the capacitor with a efficiency greater than 50% and increase the value of capacitance. So this figure actually shows uh, the difference between different materials energy density versus power density. So in order to accomplish performance beyond the limitations of each material, mainly in terms of energy density and durability, composite materials have been implemented, most of them being the combinations of carbon-based materials and other components. So here is a single electron microscopic images. Basically, these represent surface morphology of the carbon materials. So it's been characterized by scanning electron microscopy. So ACM images of carbon materials are showed here. The activated carbons prepared by carbonization of commercial lignin demonstrated the ball-shaped morphology with visible pores, while in Norit GSX image, some traces of precursor are well visible, and multiple carbon nanotubes form a cluster of irregularly shaped, which looks like natural sea sponges. And activated carbon has a large number of micropores which have influence on significant specific surface area. It's more than 2300 uh, meter square per gram, so significantly large. So here are the figures when we use 3D conductive wrapping of graphene or manganese dioxide nanostructured electrodes with carbon nanotubes or conducting polymer. So we can optimize the electrochemical utilization of highly insulating manganese dioxide materials and greatly enhance their supercapacitor performance. Comparison of cycling performance for three hybrid system here showing capacitance retention of 93%, 96% and 95% after 3000 cycles of charging and discharging at current density of 1 milliampere per centimeter square for GM, GMC and GMP respectively. So here is a figure which actually represent the capacitance versus frequency dependence of activated carbon in different electrolytes. The highest values of conductivity were obtained for 1 molar sulfuric acid and 6 molar potassium hydroxide, while magnesium sulfate has the lowest conductivity from electrolytes which were selected. For activated carbon, the highest capacitance values were obtained in 1 molar sodium sulfite solution, although that electrolyte has more than 4 times lower conductivity compared to 1 molar sulfuric acid and 6 molar potassium hydroxide. So we can conclude like this. To determine supercapacitor's performance or capacitance retention, conductivity of the electrolyte solution is not only the factor. Suitable porosity, matching the real size of the electrolyte ions to the pores of the electrode material, is also important. Thank you. Here is the reference that I have been used in the slides.